Hello, my name is Mark DeZeus. I'm a professor of civil and environmental engineering at Duke University. Co-performing with me is Professor Lee Ferguson. He's an analytical chemist, also in the same department. And the project I'm going to talk to you about today is an ESTCP project ER20-5350, titled Supercritical Water Oxidation for Complete PFAS Destruction. This project is about using this emerging and novel advanced oxidation technology called supercritical water oxidation, or SCWO in short, to destroy PFAS, primarily in rinse states, from decontamination of equipment. And we're going to tell you about supercritical water oxidation, about the project objectives, and what we have obtained so far. So first question is, what is supercritical water? If you look at the right-hand side of this slide, what you see is a phase diagram of water. And if you take water and you heat it above 374 degrees C, roughly 705 degrees Fahrenheit, you compress it to above 218 times atmospheric pressure, or roughly 3,400 psi. The water becomes supercritical. It is not a gas, it is not a liquid, it's somewhere in between, and it has amazing properties. If you have any organics in the water, and you inject air or oxygen as the oxidant, what happens is that you have extremely fast oxidation reaction. And these happen in the supercritical water phase. Some of the characteristics of SCWO are shown on the top right. The reactions are extremely fast. They occur just in a few seconds. They're very complete, and they end up in the mineralization of all contaminants. CO2 is the end product, and some mineral salts as well. SCWO is good for all kinds of organic contaminants. We say it's waste agnostic in the sense that it doesn't discriminate. It's good for PCBs, for chlorinated solvents, for fecal sludge, for biosolids. And this project is about showing that PFAS can be treated that way. And we have good evidence that it's very effective at destroying PFAS. There's no byproducts coming out of this process, no secondary untreated waste. We don't form any NOx or SOx because the temperatures are low enough. And another advantage is that the waste can be treated as an aqueous phase or as a slurry, and the process is very scalable. We can make standard scale up and imagine treatments at a large scale. So the objectives of this project are twofold: show and demonstrate effective treatment for PFAS, primarily in rinse states, and optimize the process, understand the conditions under which PFAS can be reduced by several orders of magnitude, and demonstrate mineralization of PFAS. And second objective is a techno-economic evaluation specific for DoD scenarios of decontamination at scale, and understand the cost and optimize the cost. Again, the reaction we are doing in supercritical water oxidation is shown below the phase diagram here. PFAS in the waste undergoing treatment, plus oxygen, we're using air. At supercritical water condition results in CO2 mineralization, breaking of the carbon-fluorine bond, resulting in inorganic fluoride, and some salt precipitates, such as in calcium or with other cations, in the heat of reaction. For this demonstration, we're using a pilot system that we have at Duke University. This pilot was built with funding from the Gates Foundation to show treatability of fecal sludge. And it's a continuous treatment. It's the most advanced treatment system in the world of this kind. It can treat about a ton per day, or 265 gallons a day. It uses air as the oxidant. It's much safer than using pure oxygen. It's fully instrumented with all kinds of sensors and a programmable logic controller, and we can feed all kinds of waste for treatability. This project started in the summer of 2020, and what we've done so far is we've cured waste. We have some rinse states from Tyndall Air Force Base, and we also have some legacy C8 AFFF pure compounds that we have treated in our system. And so far, we've shown that we can treat a relatively concentrated solution, 300-fold and 30-fold diluted AFFF, with excellent destruction of PFAS. With greater than 95, 98, sometimes even 99% elimination when measured as total organic fluorine. We've also measured the gas emissions, and we've seen that there's no emission of low molecular weight PFAS or any volatile PFAS. Our economic analysis so far shows that this process is extremely promising, and it could be very competitive with other technologies. We also engaged in various technology transition activities. We're producing information for the general public and different stakeholders. We're also accepting different ways, PFAS ways, for treatability studies, and are actively preparing for commercialization of this technology.